last question from hypothesis testing B. It's basically a question where you go through the entire process from start to finish. And when you do a WebAssign, they mix and match the questions a lot. So you just have to, read and see what they want. But essentially in this story, this is the question here. They got 210 students and they measured their left and their right foot as accurate as they can to the nearest millimetre. Not a very interesting thing to do, but anyway, they did it. And they found that 117 out of 210 had feet that were the same length. So evidently there are some people where their left or right foot is maybe 1 or 2 millimeters longer than their other one. That probably doesn't really affect anyone, but evidently that's something that's true. And they ask, based on this survey of 210 students, is there convincing evidence? I would say significant, but that's my phrase. Is there convincing evidence that the percentage of students whose foot length are the same differs from a half? Okay. And we're going to use a significance level of 0.05. If nowhere in the question do they actually tell you alpha, assume that it's 0.05, because that seems to be what they do. And so they give us a kind of they call it the 5-stage process. The first thing they ask you, which is exactly what you should ask, is what is the null and the alternate hypothesis? So we're interested in, is it differs from a half? So you're saying the percentage of people whose feet are the same length is not a half, differs, not equal to. And that guy up there is always the same number but equals to. So the null hypothesis will always be P equals, the population proportion equals a number, in this case 0.5. And this one, the alternate, is based on that word. If they went and said, is there evidence to prove that it's more than a half? The alternate would be P greater than 0.5. If they said it was shorter, less, some phrased it like that, than a half, you would do P less than 0.5. If they change that 1/2 to any decimal you like, then these two would change to that other decimal. So that would be your first phase. Now, we shouldn't really do a hypothesis test unless you're allowed to. So what we do next is we do the test. And the test is the 10 test. You calculate NP0 and N1P0. And there was 210. I can get that from here. So 210 times 0.5 P0. That guy there is P0. And that ends up being 105. And basically this one's 210. If you take, well, because that's 0.5, taking 0.5 away from 1 still gets you 0.5. And are these two guys greater than or equal to 10? And the short way that I do that is, did at least 10 people say yes? And did at least 10 people say no? So we are good to go. We'll assume that it's unbiased sample and that everything else is fine. So just noticed a couple of people coming in, so let them join us. Okay, for those who've just joined us, a very quick summary of what you just missed. We're doing one more question from hypothesis testing B. And this is a story about people's feet. They measured them, and out of 210 students, 117 had feet the same length, and we're being asked, is there enough evidence to show that the percentage of people who have the same length differs from a half? And the first step was the null hypothesis. It's equal to a half, and the alternate is it's different, not equal to a half. We're doing a test that we're actually allowed to do the hypothesis test itself, and that's the 10 test. So n times this number p0 and n times 1 minus this number p0. Both of those have to be greater than 10, and they are. And the yes there is just my shorthand for when you do the 10 test, did at least 10 people say yes, and did at least 10 people say no? And if that is correct, then you're good to go. Then the next phase of the process, they don't tell you all the details. They just say this phrase. They ask you to calculate the test statistic. Now that phrase is what we call the Z-score. So I want you to imagine that when they say that, they have just said, calculate the Z-score, because that's what they want you to do. Now, to calculate the Z-score, we have to do a fair number of things first. Well, I need p hat, which is 117 out of 210, but it's probably a good idea to turn it into a decimal. So 117 divided by 210, and it's 0.557. I'll also need to get the standard error in order to get the Z-score. And the standard error is the square root of p0, 1 take away p0 over n. In this case, it's going to be 0.557. If you take this away from 1, you get 0.443, and you divide everything by 210. I'll go here, and we'll go square root 0.557 times 0.443 divided by 210, and the answer I get is 0.034.
Wouldn't P not just be 0.5?
And you are totally correct. What number did I just use?
You use P hat.
I do. Can you see how easy it is to screw that up if you're too busy thinking of the next step? So let's see what that ends up in. So it's a square root, oops, clear. So it's the square root of 0.5 times 0.5. I don't know how many times I've probably mentioned that. Yeah, I still managed to do it myself. And the answer is 0.03435. If you round it off. So, I mean, it is different, right? It's not a lot different, but nonetheless, it is different. So it's important that you use the correct values. So now, to get the test statistic, the Z-score. There are lots of formulas that we have been collecting through this 9 weeks. And it is a good idea if you can memorize as many as possible. Some are used a lot, and therefore you probably should memorize them just because they're so frequent. Does anybody remember the Z-score formula that we use in these questions?
Is it p hat minus p naught over the standard error?
You nailed it. That's exactly what it is. So p hat is, make sure I put the right numbers in the right place, 0.557. P naught is 0.5 divided by the correct value for the standard error. And we'll get a z-score. Low bracket, 0.557, take away 0.5, all divided by 0.035. And the answer I get is 1.629. There we go. So all of that work there was so that we could calculate this, the test statistic. And we're good. So the next thing they ask us is to find the p-value. And it's going to be the probability. Well, if this was prove that it's greater than 0.5, we would do the probability that you get a z-score greater than that. If this had said p was less than 0.5, we'd do a probability you get a z less than that one. But when it's not equal to, you're trying to find a z less than this one and or greater than that one. And that is done, thankfully, by using WebAssign. So here we go. Are you all looking at SALT? This cell up here is a distribution. So make sure you click to distribution because it kicked to that one for some reason. Distribution calculation. Normal distribution. It's a z-score, so the mean is 0 and 1, so typically you won't change anything. We want a both tails one. A not equal to is a both tails one, right? And we wanted our number to be 1.629. So you make each side, on this side, the negative 1.629, and on the other side, you make it plus 1.629. And click out of that, and the answer that we have ends up being 0.103. And that's how you get a z-score. Just pick whatever version of the hypothesis test you happen to be in. In this case, we're in the not equal to version. Here's our p-value. And close that off. Okay, so what we're looking at now is essentially the conclusion. And in this particular one, it's one of those pull down choices things. So it has a sentence that looks something like this. The p-value is, and then I'm picking the pull down. Right, let me show you. I think it's easier if I just fill it in than to write it down. That way you can kind of see what all the choices are as well. So here we go. So the p-value is, that's this guy, it's greater than the 0.5, that's 0.05 significance level, the alpha. So there is not sufficient evidence to conclude, and you're finished. Now, if my p-value, let's pretend the p-value we got was 0.0103. Then you would have said the p-value is less than 0.5, and so there is sufficient evidence, right? So you either go left or right. Okay, there is evidence or there's not. Do we have any problems with that process? Do we feel comfortable about it? That is maybe a good template for every hypothesis test that you're likely to come across. So now we're on to the last part of chapter 12. So we're going to be looking at hypothesis testing for the difference between two proportions. That's a mouthful. It's really just an extension of what we've done. And this is also part of chapter 12. And when we finish this, you'll have covered everything that you need for the online homework 9. So what makes it different? Well, it's a difference between two proportions. So this is a hypothesis test that you have two distinct populations. Right, so we have population 1, and over here we have your other population 2. And we are interested in, is there any difference between the two? So let's get terminology. P1 and P2. P1 is going to be the population proportion. For population 1. And P2 is going to be the population proportion for the other one, population 2. Okay, let's put a story with this. Population 1 is going to be Scotland, as I want it to be, and population 2 is going to be England. And you ask each people from each population, you ask them something and you get a certain percentage of them will say yes. So let's suppose the question that we asked them was, do you like whiskey? And we take a sample, and the sample N1 is the sample size. And P1 hat, in this case, was the number of people out of, how big shall I do my sample? Let's put numbers in it. I take 100 Scottish people, and I found out that 62 out of 100. So 62% of adult Scotsmen said, yeah, they like drinking whiskey. And then they went over and they did the same question. And they asked it English, and N2 is going to represent the sample size of that group. And in the English, we asked a lot more. We asked 250 of those. And out of that 250, let me pick a number. $155 of them, which is no, not 155. Make it 150. That's a nicer number. 150 of them said that they liked whiskey, which ends up being just 60%. Just like we do in all things, you could say, well, I think I've proved what I was expecting. Scots people like whiskey more than English people, right? 62% of Scot, a little bit less for English. But we know that when you do samples, they vary. And could that one be a little bit high and this one be a little bit low, and actually both of them were 63, or both of them were 82, that'd be unlikely, but they could be the same. And in another world, could actually the English like it more than the Scottish? Maybe the Scottish was 59 and the English was 61, right? So because you know there's variation, this raw data is not evidence yet. We have to set up a formal hypothesis test. And the hypothesis test is similar to the ones we've done, but it's not the same. You have a null and you have an alternate. The null hypothesis is always the same. And that is that the difference between the two is 0. In other words, you always assume that both groups are the same, right? That's the simplest way of doing it, right? They're both the same. And then you have an alternate. And the alternate hypothesis, and there are 3 of them, so I'll put little boxes around them. Here they are. One of them is that P1 take away P2 is greater than 0. What situation would you be looking at that? Well, that would be if this guy was bigger than that one. When P1 take away P2 be positive, if this population proportion was a larger number than this, right? Big guy take away a smaller guy, positive answer. Second version is that it's equal to 0, and the alternate is that the difference is a negative number. And what would that look like? Well, that would happen when this one is less than that one. Does that make sense? Now, do you notice that there are no 0.6s or 0.5s or point anything? Do you notice it's zeros all the time? That's the difference. You know, when you do a one proportion, don't you have P equals 0.7 and the alternative P is bigger than 0.7, right? You have a decimal, a guy called P naught, right? Every time. In these ones, you see, they always revert to 0. I said there's a third possibility. The null hypothesis is that both are the same, and if they're both the same, the difference is 0. So that's a right tail test, that's a left tail test. They just call that a one tail test. What's the last one going to look like?
It won't equal 0.
And you now have all 3 possible things that you can have when you're doing a hypothesis test for the difference between 2 proportions. You either have the difference is 0 and the alternate is it's bigger than 0. Second one is that the null hypothesis is the difference is 0 or that it's less than. And the last one, the difference between them is different, right? It's not 0, right? They're different in some way. Are we good with this? Now, we have a test that we don't use much, but we have used occasionally in the one proportion, and it's the same for this fella. It's just a lot more things to check. So what is your test? Is the data random? Is the data unbiased? And does it pass the 10 test? Right, we'll just assume, because there'll be no evidence, I think, that those 2 are not what they should be. The 10 test looks like this. Each one gets tested. N1 times P1 has to be greater than or equal to 10. N1, 1 minus P1 has to be greater than 10. N2, 1 minus P2 greater than or equal to 10. And N2, P2. No particular reason why I did them in that order. Can you see you have to check all of them? those are population 1, those are population 2. So think of it like, did at least 10 people say yes and at least 10 people say no from the Scottish population? And did at least 10 people say yes? Oh, that's the wrong one. No and yes. Right, I should check it on this one now. Let's see what we got. If we do the Scots population first, right? Population 1. Didn't 62 people say yes, and that means the other 38 said they don't like whiskey? Would you agree that passes the 10 rule? I'm not even doing the calculation, because if I've got the raw data, I can figure it out that way, right? If we take the second one, which is the English population 2, 150 of them said yes. And what would that leave? That leave 100 said no. Would you agree that passes the test? That's just basically making sure your data is big enough, right? Nobody should ever make a decision based on 4 English and 3 Scottish. Would you agree? It'd be a pointless exercise. So it's there to stop us from doing things we shouldn't even think about doing. Are we comfortable about that then? So I guess I'll put, there's A, first thing. There's B. Hypothesis test and this. And now that I've thought about that, there's something missing from here. And that is a significance level. And it can be 0.1, 0.05, or 0.01. And since this book has almost no imagination, they're using 0.05 in virtually every question I could find, which is fine. But sometimes they don't mention it because it's just, we're using it all the time, they don't say it. But strictly speaking, this should be written down as part of the question. So far, so good. So where do we go next? Well, call it C, ABC. We have to calculate what they are calling the test statistic. I call that guy the Z-score. Well, not just me, but other people as well. So, similar in a lot of respects, but also a little bit different. For instance, we're going to calculate the difference between the two. Does that make sense, that if you're trying to figure out what the difference is, you should be using the difference of these samples? So that guy, right, difference between one and the other is what? 0.62, take away 0.60. So the difference is 0.02. And we should be finding the standard error. Now, when we did a single proportion, this would be P naught, 1 minus P naught over N. But when you're doing a difference between two, there is no P naughts to use, right? There is no value from the proportion. There's only these guys. So the formula can you remember doing confidence intervals for the difference between two proportions? Isn't that the same standard error formula, right? So that's a lot messier than it was earlier. In this case, that's going to be the square root of 0.62, 0.38 divided by 100 plus 0.6 0.4 divided by 250. This is actually for unpooled data, right? That's the only one you need to worry about. So let's put that together. Square root 0.62 times 0.38 divided by 100 plus 0.6 times 0.4 divided by 250. And the answer I get is 0.008, round it off to 3 decimal places. Now, we haven't got to the test statistic, but we need to know this number and we need to know that number to get the test statistic. And the formula for the test statistic, called the Z-score, P1 hat, take away P2 hat over the standard error. And the difference between the two was 0.02. And this guy was 0.058. So we are going to get 0.02 divided by 0.058. And we're going to get 0.345. Are we good? Would you agree, just looking at that, that is not a very good Z-score for evidence? You want a really big positive or negative Z-score, right? You want a 3.7 or a minus 2.9, right? You want those kind of numbers. That one is probably not going to be very significant, right? So it looks like we won't be able to prove that Scotsmen like whiskey more than English. So where do we go next? Well, the next stage, step D as I'm calling it, is we are now going to find the p-value. And the p-value is a probability that you get Z-score. And let's return to our story. I forgot what I was asking. Oh, I want to prove that Scotsmen like whiskey more than English, right? So we were going to do that one, right? They're the same. Scotsmen like it, whiskey more than English. So since we were doing a greater than, that's going to be your p-value. If our story was prove that the first one was smaller than the second, Z-score less than that. And if we were proving it was different from the other one, we'd have to do one of those two-tail things. But that is essentially going to be done using salt. So I'm setting that up. We should be ready for it. So here it goes. Close this window and open another one. There we go. So click on distribution. There we go. Leave these as their standard values. We want a greater than, so I'm going to pick right-tailed, right? Bigger than. And we want to find, is it bigger than 0.345? And the answer you get is a p-value of 0.365. And that's us calculated the p-value. Right. Pretty easy to do. Calculator really, the software does it all for us. E, we now do our test. Our test is the p-value less than alpha? And in this case, is 0.365 less than 0.05. I think that's a pretty obvious answer, isn't it? It's not. It's not. What conclusion do you come to then if the p-value is not less than alpha? Well, you can phrase it all sorts of ways, but here's one of them. There is not enough evidence to reject the null hypothesis. So we don't know if Scotsmen drink whiskey or like whiskey more than English. We just don't have enough evidence to make that decision. And that is a pretty much how the whole process from start to finish works. From two populations to choosing which one of these three you're interested in proving, to doing all the tests to make sure you're allowed to do the hypothesis test, to calculating eventually the z-score after a few other things, to then using salt to get the p-value. You then test, is your p-value less than the significance level of 0.505? And if the answer to your test is no, not enough evidence, if the answer to this was yes, the p-value is smaller than that, you would then say there's enough evidence to prove that the alternate is true, would be one of the phrases you could use. Any questions about that process? I think we have time to do one with the class. So I'm going to collect some data here. 1, 2, 3, 2, 5, 10, 15, 20. So I'm going to pretend that you lot are one person. You lot are really 10 people, just so that I can get by step 2, right? Because if I don't, I won't even be able to use hypothesis test. So we're going to have population 1, the self-identified males. Population 2 is going to be the self-identified females. So first thing I'm going to do is count how many guys there are. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there's really 80 males. And 2, 4, 5, 10, 15, 19. That's 11. And there is 100, allegedly 110 females. Okay. So what we're going to ask is a question. Anybody got a question that would be easy to answer yes or no to, and wouldn't be that personal that you would, that people wouldn't mind answering it? Anything you want to know about this class? No.
Oh, sorry. I was having internet problems and I temporarily got connected out.
Okay. Okay, I'll ask you. How many? This is only for the guys. So you know that little thumbs up button that you can do in reactions? That guy there? Right. So that's how you can vote for me. How many of you have been to a foreign country? And I make that 5. So that's 50 out of 80. Okay. Okay, the females amongst you, how many of you have been to a foreign country now? So Raven, you can vote again. How many of you have been to a foreign country? Cool. I got a nice discrepancy in the data. I make it 2, so that's 20 out of 110. So we have collected our data in a very unscientific way, but we're going to pretend that we collected it in a really good way, right? So based on the numbers that we've got, I'm going to turn them into decimals. So 50 divided by 80. 62.5% of the males have been to a foreign country, and 20 divided by 110, and only about 18.2% females. So significance level, I'm going to go for 0.1, which is the strongest one. That's the hardest one to win with, right? Really hard. And I'm going to go and assume that males have been to foreign countries more often than females, right? That's the difference. More males than females. So our null hypothesis is that P1, males, take away P2 equals 0. Well, by the way, that is exactly the same thing mathematically as that, isn't it? And so you might see some textbooks where they write this instead of that. Right? It's no biggie, it's the same information. Now, the alternate is that the difference between the two of them is actually greater than 0. In other words, males are, there are more of them proportion-wise than females. And if you were doing it this way, that's exactly the equivalent mathematically to that. Would you agree? Same thing, right, in two different ways. This is the way we're going to do it. Technically, that's A done. B, I'll just talk through it. Yes, there was at least 10 people who said yes, and at least 10 people said no in every group. So we know that that's done. Okay, move on to C. We have to find that, which in this case is 0.625, take away 0.182, and 0.625, take away 0.182. That's a pretty big difference, isn't it? About 44+% difference. So I'm very confident, I've been proved wrong in the past, that we're probably going to get significance here, right? We're going to be able to prove that it's true. Carrying on with that, the standard error, that's the ugly calculation, that big thing there, is P1 hat, 1 take away P1 hat, over N1, P2 hat, 1 take away P2 hat, over N2. It's going to be the square root of 0.625. So 0.625 times 0.375 divided by 80 plus 0.182 times 0.818 divided by 110. And we got 0.065. So our Z-score, called the test statistic, is the difference in the proportions divided by the standard error. And the difference was 0.443 divided by 0.065, 0.443 divided by 0.065, and I get a Z-score of 6.815. Now I'm going to be doing this guy on salt, but I can tell you right now, I know the answer. Aren't Z-scores of 3 outliers? That's how unusual they are. Isn't a 4 like 10 times rarer? and a 5 is 10 times rarer than that, and a 6, but that's almost 7, is even rarer than rare, right? That's like finding a politician who tells the truth and doesn't leave the government with more money than he started. There's a surprise for you. If you're interested, find out how much all your politicians are worth. Find out what they were worth before they became a member of Senate. And almost to a man and woman, they're worth a lot more money. Now, since I don't like politicians, I suspect that they might be getting money based on their job. And that doesn't mean that they do it illegally. They're far too clever to do it illegally. They just do it legally. Right, so we got, hopefully you can see it. It's set up here, normal, blah, blah, blah. We want a greater than, that's all set up. The number I want is 6.815. And do you see that little warning sign and a 0 here? That's just the software getting annoyed. It should be a number greater than or equal to that, and it lies in less than equal. It's basically just saying the answer to the p-value is 0, or at least to 6 decimal places 0, right? So it's darn close to being perfect. So time for our test. Is our p-value less than the significance level alpha? Is 0.00000, but is 0 less than that one? And the answer is yes. So the conclusion will be, if your p-value is less than this number, there is enough evidence to prove that HA is true. So if we'd conducted a real sample, I'm not quite sure where I would publish this data. I'd put it in a magazine probably, if they would buy it. I could say, for some reason, guys go to foreign countries more than women.